So good morning, friends. Welcome to Water Resources Engineering class. So we are now dealing with the fourth unit, groundwater hydrology. In that groundwater hydrology, we have completed the definitions of it, the groundwater occurrence part, and then actually the aquifer parameters, types of aquifers. Then we have taken up the Dupit's theory. Then we have taken up the unconfined aquifer. And before Dupit theory, we have taken up Darcy's law. So all these we have completed in the previous lectures. Today's lecture is focused on, once again, just refresh you on Darcy's law, Dupit theory, assumptions, and straight away let us go into the study radial flow to a well in a confined aquifer. Unconfined aquifer we have finished. Today we will go to confined aquifer. But just refreshing the first three, that is Darcy's law, Dupit's theory and its assumptions, very fast. Let us quickly recollect and then move forward. So Darcy's law, already we have mentioned that it is nothing but actually it's in the discharge per unit area is proportional to the hydraulic gradient. That's all what the Darcy's law says. That means the Q by A, which is also called as the velocity, is proportional to the hydraulic gradient. So Q by A is proportional to I, or Q is proportional to IA, or Q is equal to KIA is the Darcy's law. And Darcy's law is the fundamental equation for the groundwater in the groundwater hydrology, especially which describes the flow in a flow of water through a porous media, right? So this is as far as the Darcy's law is concerned. Then after the Darcy's law, let us go into the assumptions of Darcy's law. Just aquifer, the medium is homogeneous and isotropic, flow is steady and laminar. Especially one of the most important thing is, please note that laminar flow. Darcy's law is applicable only for laminar flow. The hydraulic gradient is more or less uniform actually, and the aquifer, the soil is completely fully saturated and the fluid is incompressible and has constant viscosity. Then coming to the Dupit's theory, already we mentioned, in the case of a unconfined aquifer, it is the water table that which we mentioned, that the water table, as we start pumping, the water table takes the shape of a cone, actually cone of depression. So the water level decreases, and how it decreases is in the form of a cone of depression. That's what we talk in the case of an unconfined aquifer. But in the case of an confined aquifer, there is nothing like any water table actually. Here instead of water table, whatever that initial level is there, what we call it as piezometric surface. So that piezometric surface actually takes the shape of a cone of depression once the pumping started, and that cone of depression is being shown in the figure which you can see here also. And that cone of depression is nothing but actually it is also called as drawdown curve. How much water level has decreased from the initial water level is the main thing actually. That is what is represented by the drawdown. Drawdown is nothing but the vertical distance by which the initial water level has been decreased, right? That is what we call it as drawdown. And that drawdown is maximum at the well actually, and is minimum as the distance from as the radial distance from the well goes on increasing, naturally that will drawdown go on decreasing. Where the drawdown is zero, that point is what we call it as the radius of influence. So this is what we have studied, and this has been explained by Dupit and then later improved by the theme actually. So it is whatever we discussed, they are all Dupit theme theory. Then what are the assumptions of Dupit theory, which is very, very, very important actually for you? Aquifer is homogeneous, isotropic and of uniform thickness, and its extension is infinite areal extent. So 4 points I put together: homogeneous, isotropic, uniform thickness, and areal extent is infinite. That is the thing. The well penetrates and receives from the entire aquifer, it receives the water. That is number 2. The pumping has been continued for a sufficiently long time so that the steady state conditions are established and steady state is reached actually. That is the third. And coefficient of transmissibility, which we in the other way, in the unconfined aquifer, we call it as coefficient of permeability, but that permeability multiplied by the thickness of the aquifer gives you the transmissibility. That coefficient of transmissibility is constant. That is what we are assuming. It is constant actually. And the flow lines are radial and the flow of groundwater is horizontal. Only lateral flow only we are considering. And flow is laminar. Darcy's law is applicable. And the hydraulic gradient may be represented by tan theta instead of sin theta, and theta is nothing but the angle between the hydraulic gradient and the horizontal. Next, last point is the well is infinitely small with negligible storage. So whatever water that is being pumped, all that is from the aquifer. The storage in the well is negligible. That is the last point actually. Very, very important, this Cupid's theory assumptions actually. Same is the case with the limitations which we talked a long time. So vertical flow component is neglected. Small drawdown requirements actually which you need to take. Fully penetrating wells only it is applicable, and it is basically generally mostly Cupid's theory is initially defined for only for unconfined aquifers, but later it is applied to confined aquifers also. The radius of influence is indefinite. That's why it is only through empirical equation you can calculate, and uniform aquifer assumption which we made it, and we have not mentioned anywhere how you are going to account for the losses. So these are some of the problems actually in this. Let me come straight away to the point actually. Right? What is that point actually? We are talking about the confined aquifer. So in the case of a confined aquifer, and this confined aquifer is also called as artesian aquifer. Artesian aquifer. Confined aquifer, artesian aquifer are similar, same. So in the case of an confined aquifer, how to derive the equation for the discharge, for the yield or discharge, both are same. How to get basically a relation or how to get an equation for the yield of a well actually which is penetrated or which is dig into a confined aquifer. That is the question actually. Last time we have derived the same thing for unconfined aquifer, but in today's class let us discuss the same with the case of confined aquifer. The difference is already I mentioned. There the water table is the starting point actually, that is the initial water level. Here piezometric surface is the initial thing. So that's why see in the figure, this is the thing. So while drawing figure also, first what you need to draw, confined aquifer you should draw. So that confined aquifer means, for example, this is the confined aquifer. This is the confined aquifer. So now here this is what confined portion. In this confined portion the water is available. So what we have done is we have dig into a well into the confined aquifer, right? And this is the ground level, right? And now we are starting pumping. The moment you are starting pumping, naturally how this will be is initially this is the piezometric surface. In the case of unconfined aquifer, what you call this as, actually this is the piezometric surface, right? Now you draw this, right? This is the cone of depression or drawdown curve actually. So now remaining, this is the radius of the well, then radius of influence, all the other things. S is the here whatever is the drawdown is there, that, and H is the remaining part. All that you can record here depending upon the given things. So these are the basic things which we know. So now let us see the figure also. Let R is the radius of the well. So what is the radius of the well? Actually this is the radius of the well. Then naturally H is the thickness of the aquifer. H is the thickness of the aquifer means from the bottom of the impervious one to the piezometric surface, whatever is there, that is what we call it as H, right? That is H. So now next, B is the thickness of the confined aquifer. This part is what we call it as the thickness of the confined aquifer. Then next one is, what is drawdown? Drawdown is how much this initial piezometric surface is decreased at the well. This is the drawdown at the well. So S is the drawdown at the well. See here, we are dealing with a confined aquifer. A confined aquifer means water is being basically flowing between two impervious layers. So this is the bottom impervious layer, this is the top impervious layer. Flow is there between this. Now we are digging a well into this confined aquifer, right? For this confined aquifer, so this one first, this dotted line is the initial piezometric surface. From the bottom of the impervious strata to the piezometric surface, we call it as H. That is what which we have taken. Thickness of aquifer is that, not this actually. Then R is what? Radius of the well. That is fine. B is the thickness of confined aquifer. This is the thickness of the confined aquifer. Then actually S is the drawdown at the well actually. Then R is the radius. That means at zero drawdown, whatever is there, this is what we call it as R. Right, next. Now what I have taken, this point like unconfined aquifer, I have taken as, this point is taken as the origin of coordinates. If I take this point as origin of coordinates, right, now basically with respect to this point, any point on this drawdown curve, I have noted it as P and its coordinates are XY, right? Next, already from Darcy's law, we know that Darcy's law is equal to Q is equal to Ki into A. That is the general equation. Now I want to apply the same here, right? Because now if you see, this is how the water surface changing. So if suppose at this point, if I take it actually, so now if you imagine this here, how it will be actually like a circle perimeter, because from here same. So this is a circle like thing. So that's why it's perimeter. And now from where water is drawn? Water is not drawn from this entire thing actually. Water is not drawn from here to P. Water is drawn only from this portion. This is the portion only where the water is available. The rest is because of the pressure here, because the water is confined between two layers. So naturally the pressure there is more than atmospheric pressure. Because of the pressure here, this is the piezometric surface. The piezometric surface represents you the hydraulic, that means gradient, that means the pressure line actually. Because of the pressure, the water level, we have shown it here actually, but there is the well is not drawing water from the entire thing. Well is drawing water only from the confined portion. So that's why. So if I take here, what is the perimeter at that place? 2 pi r. 2 pi r means x is the radial distance. So 2 pi r is the basically the first perimeter multiplied by the vertical distance, the y component. But here y component is not from here to here. The y component is only the thickness of the confined aquifer. That confined aquifer thickness is B. Why only B should be written? Because water is drawn only from that depth. Remaining all, there is nothing, no water is there, and well is not drawing water from that area at all. So that's why total area of cross section, if I take it, it is 2 pi x into B. Then next, what is hydraulic gradient? Hydraulic gradient is nothing but the slope of this line. That slope of that line is nothing but dy by dx. So therefore, Q is equal to K into I is dy by dx into 2 pi xb. So therefore, now what we have done in the previous case also, all x's on one side, all y's on the other side. The same thing which we have done. So that's why we brought actually, this is denominator. So if it go to left hand side, Q into dx divided by x is equal to K into 2 pi b into dy. So this is what. So why I have done that? Only to integrate all the terms related to x on one side, all the terms related to y on the other side. That's what precisely I have done here. Then integrating this between the limits r to r for x and h to h for y, then what we will get actually. So why r to r I should see? If you see the x limits, x limit is from the center. If I take it, naturally r is small r is the radius of the well, that is the starting thing actually, and capital R is the radius of influence maximum actually. One is at zero drawdown, one is at the maximum drawdown. So that's what, how this r and r has come. Similarly, what is capital H and small h? Small h is the actually the water level in the well actually when pumping start, after pumping. Then what is capital H? The piezometric surface at zero drawdown, that is first thing. So that these are the limits actually from small r to capital R, from small h to capital H, that I have put it here, and the same thing we have basically integrated the equation. When we integrated the equation, we get 2 pi kb into h minus h divided by log r by r base e. Then this log, basically I will convert this also. If suppose you want to convert log e to log 10, then you need to multiply this actually into 2.303 and pi is 3.14. Put it that and then simplify this equation. So we have taken the same thing. So log e to log 10, if I take it here, 2.303 and pi is basically, so if you to 3.14, so if you do it, you are going to get 2.72. Same in the case of unconfined aquifer. If you remember, there this 2 is not there, because of that you got 1.36, whereas in the case of confined aquifer, it is instead of 1.36, it is 2.72. 2.72 kb into h minus h divided by log r by r base 10. So this is the basic thing. And now actually if I take it, what is h minus h? If you see, h minus h is nothing but s. So that's why h minus h is equal to drawdown. So that's what I have put it here. You can see the figure and confirm actually. Then what I have done, 2.72 kb into s divided by log r by r base 10. This kb is also called as transmissibility. So that is the next. So instead of kb you can substitute t. So thereby you get 2.72 ts divided by log r by r base 10. So this is what we call it as the theme equation or equilibrium equation for steady radial flow in a confined aquifer, and this is the thing. Whereas there actually h square minus h square we got it actually, right? Here it is only h minus h. So that is the differences you should understand. There 1.36, here 2.72. Suppose if h1 and h2 are the measured depth of water in two observation wells situated radially at distances r1 and r2. So that means if suppose I take it, suppose this is your confined aquifer. You can draw the figures very easily. Now what I have to do, I penetrate a well into it. Then this is what? The ground surface. Right? This is the piezometric surface. Now if I do it actually, so this is the thing and this is the thing. This is the cone of depression. So now what I can say, this level is small h and this is s actually, am I right? And this is capital H and this is B, right? And now we have two observation wells. So one observation well I have taken here and one more observation well also you have taken here. So this radial distance is R1 and this is R2. That's what I have written. In such a case, actually, this is H1, this is H2. That's what I have mentioned. In that case, instead of H minus H, we can write it as H2 minus H1. That's all the only difference. So this is useful for solving many problems actually to you. So now completed actually. Finally, what is the equation? Q is equal to 2.72 kbs divided by log r by r base 10. This is the fundamental equation. This kb also you can change. Q is equal to 2.72 into T into S divided by log R by R base 10. That's all basically here. Now, how to determine this aquifer constants actually? This is the thing. So, aquifer constant is the transmissibility. How to determine that transmissibility? So, for a confined aquifer, I will just show you the path actually. Right? Normally, this transmissibility T can be found out by pumping test. Pumping test at various observation wells in the aquifer. Aquifer may extend several kilometers actually, several square kilometers area, right? When such an aquifer, big aquifer is there, so how to find out the transmissibility is you dig observation wells at different places, and in all those places, if you conduct pumping test, then you can find out what is T value. That I explained. You can see it. The aquifer constant T can be determined by pumping test and observing data at various observation wells in the entire aquifer. Pumping must continue at a uniform rate for a sufficient time. What for a sufficient time is to reach to the steady state conditions, because whatever we are studying is only steady state. So in order to attain the steady state condition, long time pumping at a uniform rate is necessary. Let S1 be the drawdown at the well 1, observation well 1. If you take it, observation well 1, if I take it, so there actually if I take S1 is the drawdown, and at number 2 it is S2. How to get S1 actually? It is H minus H1, and how to get S2? H minus H2. That's all basically. So now if this is the case, now from both of them, what is H2 minus H1? You tell me. H2 is what actually? If you take H minus S2 actually, it is equal to H minus S2, right? And this is what actually? H minus S1. So finally what it will be? H minus S1 minus H minus S2 will be the thing, H2 minus H1. So that is what I put. And finally H2 minus H1 is equal to S1 minus S2. So instead of H2 minus H1, you can write basically S1 minus S2. So general equation is what? 2.72 kb into S. S is what? H minus H divided by log R by R base 10. If observation wells are there, instead of H minus H, you write it as H2 minus H1. Here you will write it as R2 by R1. Right? That is the basic thing you will do. Right? Here what I told, instead of writing H2 minus H1, why don't you write in terms of drawdown? That in terms of drawdown is S1 minus S2. That is what precisely I have put it in the equation. So 2.72 T into S1 minus S2 divided by log R2 by R1 base 10. So what is T is equal to? So T is equal to, if you take all this left hand side, T is equal to Q into this divided by 2.72 into this. So now what we assume it. For example, if I assume basically R2 is equal to 10 R1. So therefore log base 10 R1 divided by R1. R1 cancel. So log 10 base 10, what is the value? Is equal to 1. That's what I have written here. So in such a case, T is equal to Q by 2.72 into S1 minus S2 into 1. That is nothing but Q by 2.72 into delta S. So this is the first thing. So finally, what is the equation for me for T to me? It is nothing but Q by 2.72 into delta S. That's all. So here Q is known quantity. only delta S has to be found out. How to find out the delta S is the one of the thing. So one example I have shown here. So but how can you find out? That's what I have written. Delta S is nothing but difference in drawdown at the two observation wells so selected that R2 is equal to 10 R1. Hence, observing drawdowns at wells located at various radial distances, a graph is plotted such that drawdown is on y-axis and log value, because it's a semi-log graph actually. Drawdown is on y-axis and log, basically Rx is nothing but R2 by R1 actually. That ratio whatever we are writing here based on x-axis. So if you plot this actually, the graph like this, then delta S can be obtained for one cycle. The moment one cycle you have taken, that's what in the 110 if I take it. So this, if you take it as one cycle, for one cycle it is shown, delta S can be obtained. Once delta S is known, you can find out T. So this is only confined aquifer I have shown. That completes to me the derivation part. And most of the information that which I have presented to you are basically either from the textbooks that they have given or from the reference books. So mainly always kindly go through the textbooks also for the more content in this regard. Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.